In the today's lecture we are going to see the leakage factor. Okay, so as you can see in the figure, there is a one electromagnet. Okay, so one magnetic core is there. Okay, and on that magnetic core there is a one wire wound over that magnetic core. It forms the coil. Okay, and if the current flows through that coil, the magnetic flux starts emitting from that coil, and it is expected that that magnetic flux must follow the magnetic core. Okay, but you can see some amount of magnetic flux is leaking from that magnetic core and taking the short path. Okay, instead of following that long path through the magnetic core, the flux is getting out of that magnetic core and taking a shortest path. Okay, and it complete its circuit. Okay, magnetic circuit. So regarding this, there is a one factor which is the leakage factor. Okay, so whatever the flux is generated in that coil must follow that magnetic core. Okay, and must cross the air gap between the magnetic core, which is on the right hand side. Okay, and the flux which is the crossing the air gap between the magnetic core, which is called as the useful flux. Okay, the ratio of the total flux produced, okay, which is produced at the coil, okay, to the useful flux setup in the air gap, or which is the useful flux of the magnetic circuit, is called as the leakage coefficient or the leakage factor, and it is denoted by the lambda. Okay, so what is leakage factor? It is the ratio of magnetic flux produced to the magnetic flux in the air gap is called as the leakage factor. Okay, so leakage factor is one of the most important factor. Okay, so the ideally leakage factor must be 1. Okay, so ideally the whatever is the flux generating from that coil must follow the magnetic core and must cross that the air gap between the which is available in the magnetic core, or the generated flux or produced flux must be equal to the useful flux. Okay, so which is called as the leakage factor. And what is leakage factor? Leakage factor simply ratio of flux produced divided by the useful flux in the air gap. Okay, then BH curve. Okay, so you can see the graph of H versus B, or magnetic field strength or magnetic flux strength versus the magnetic flux density. Okay, which is called as the BH curve or the magnetization curve. So H is plotted on x-axis and B is plotted on y-axis. So it is the graph of H versus B, or B versus H, which is called as the BH curve or the magnetization curve. Okay, so from let us understand that graph from 0 to A. Okay, so at the value of H, which is equal to the 0, or if the value of magnetic field strength which is equal to the 0, the magnetic flux density is also 0. Okay, and as H starts increasing, there is a small increment in the value of B. Okay, so up to the point A, so it is called as the non-linear region. Okay, so there is a large increment in the value of H, there is a small increment in the value of B, so it gives us the non-linear region. Okay, or non-linear zone from O to A, or a 0 to A. So point A to C, so there is an increment in H. Okay, there is a linearly increment in the B, so it gives us the linearly proportional graph, or it gives us the linear relationship between H and B. Okay, so it gives us the linear zone. After point C, okay, after increment in the large value of H, okay, there is a smaller increment in the value of B. Okay, so it gives again the non-linear region. Or after certain amount of, or after certain the value of H, the value of B does not increases. Okay, so that region beyond C, okay, which is called as the saturation region, or saturation zone. So what happened in the saturation zone? If the increment in the H, there is a smaller increment in the B, okay, it gives us the nonlinear region. Or after some value of H, okay, beyond some value of H, the increment in the H, there is no increment in the B, okay, that's why it is called as the saturation region or the saturation zone, and that graph is called as the BH curve, okay. So hysteresis loop, okay, so in the hysteresis loop we have plotted that H versus B, okay, but for the positive value of H as well as the negative value of H, okay. So BH curve is only for the positive value of H, and hysteresis loop is for the positive value of H plus negative value of H, okay. So that dotted line in the hysteresis loop is the BH curve. So from incrementing of H from 0 to some value which gives us this dotted line up to the saturation point A, okay. So from saturation point A, if we decrease the value of H to the if we decrease the value of H to the 0, okay, the value of B we get from, or graph we get from A to B, okay, and for the value of H which is equal to 0, we get the some value of magnetic flux density which is called as the retentive point B, or which is called as the residential magnetism, okay. So for the value of 0 magnetic field strength or magnetic flux density, magnetic field strength, we get the some value of magnetic flux density which is called as the residual magnetism, okay. So for the value of H, okay, which has the value of 0, we get some value of magnetic flux density B, okay, and to decrease that magnetic flux density B to the 0, we have to reverse the direction of magnetic field strength towards the negative direction, okay. So we get the negative value of H up to the point C, we get the 0 value of magnetic flux density, okay. Again we decrementing the value of H, okay, to the point D, okay, we get the graph of C to D. Again we starts decreasing the value of H minus H towards 0, we get the graph of D to E, okay. For the value of magnetic field strength which is equal to the 0, we get the again negative magnetic flux density which is also the same value of B, okay, but opposite in polarity or opposite in direction, which is called as the residential magnetism. And to get that residential magnetism 0, or to nullify that residential magnetism, we have to increase the magnetic field strength to some positive extent or to the point F, okay. So that closed path from A to B, B to C, C to D, or D to E, E to F, F to A, that A, B, C, D, E, F, A closed path is called as the hysteresis loop, okay. So difference between electric and magnetic circuit. So up to this point we have understood the basics of electric circuit as well as the magnetic circuit. So now we can understand the differentiation between them. So on left hand side there is electric circuit, on the right hand side there is a magnetic circuit. So electric circuit has a component resistor or any kind of basic components, resistor, inductor, capacitor, okay, and in the magnetic circuit it has the magnetic core and one coil wound on it. So EMF is the source to pass the current. Okay, if you want to pass the current through the circuit, we need the electromotive force, and EMF is the source to pass the flux. So if you want to pass the flux through the core, then we have to generate the magnetomotive force. Current can be measured in ampere and current density is ampere per meter square. So flux can be measured in Webers, or flux density can be measured in a Weber per meter square. So current is the EMF upon resistance and flux is the MMF upon reluctance. Resistance R is equal to del or rho L upon A, and reluctance is equal to L upon mu 0 mu R into A. Conductance is reciprocal of R. Permeance is the reciprocal of reluctance. Energy is wasted as long as the current lasts. As the current flows through resistor, there is a wastage of energy. So energy is required to establish the flux only and not maintaining it. So to maintain the flux inside the core, there is a requirement of energy. Okay. After maintaining a flux, there is no longer need of the energy. No leakage of current. So current only follow the path of conducting line. Okay, current cannot be leaked through that line. There is a leakage of flux. Okay, through from the magnetic core. Current can be insulated, that is cannot pass through all the mediums. There is no magnetic insulator. The flux passes through all the mediums. So current flow is the true flow. There is no actual flow of the flux. Okay, so that is the difference between electric circuit and magnetic circuit. So with this we are going to stop here.